There are several, or at least a couple different kinds of line integrals. Okay, one type of line integral is a line integral over a curve C of a function f, but that function f is a scalar function. Okay, and a scalar function, by that we mean a function, say, of two variables f of x, y, or perhaps even a function f of x, y, comma, z. So these are just the kinds of functions that we have been looking at throughout the semester. So one example of a function, a scalar function, is x plus the square root of y. And the curve C could be the curve that's made up of this parabola, this parabolic path, and this line path. So our curve C could be the part of the curve that is this part of the parabola, and then you end up at the point 1, 1, and then you come backward to 0, 0 along this straight line. So together, those two parts of the path make up the curve C. So there is a path C1 and then a curve C2. Okay, in this video we'll just discuss the meaning of this an integral of this type, and then in follow-up videos we will actually go through the evaluation of that. So what we're seeing over here to the left is a plot of the function x plus the square root of y as a density function. Okay, as a density function, we can see that, for example, if we put in the point 1, 1, then we'll get 1 plus the square root of 1, which is equal to 2. And that number 2, right here at this point, there is a number at that point, and that number 2 represents the density at that point. Okay, so we can imagine that we've got a square grid, right? That's what we were seeing in the picture over here to the right. And at every point that you pick in this grid and plug in that number, that point, you will get a number, and that number represents the density of the material at that point. So we're imagining that we're having like a sheet of paper or something, but this sheet of paper is not just an all uniform piece of material that maybe at some point, like at this point here, right, we can see that in the plot right there, it's kind of orangey, and then this plot over here on the left, you can see that the color at that point is kind of orange. So this is a region of maybe medium density, right? And then there is a red point here. If you pick the function at that point, right up here in the upper corner, it's red. That is the highest density. And then maybe you've got this material down in the lower left corner, right? The function at 0, 0 is 0, and that's why our density, that is a region of low density. Okay, so when we are computing these line integrals, when you do the line integral of the curve of this density function, right, you're actually going to compute the integral over the first part of the curve, which is the parabola path of this function ds, and then you're going to add that to the function, the line integral on the second part of the path, which is this straight line, right? And the interpretation of each of those integrals is that it would be the mass of this first part of the curve C1, and this would be the mass of the second part of the curve C2, right, with density function f. And so by evaluating these integrals, we are finding the total mass that if you were to have this square region made out of certain material, and then you were to come in and cut out these little lines here, cut out this path, right, we would then figure out how much that curve weighs. Okay, So that is the interpretation of these line integrals, but of scalar functions as density functions, and doing these line integrals, how they will give you the interpretation of mass. In the next video, we'll talk about how do you actually evaluate these line integrals, and they are evaluated by doing the integral t is equal to a to t is equal to b. So here along the parabola path, you're at one point at time 0, and you'll be at the other point at time 1, and the parameterization of that path would be t comma t squared. So you'll find the density function along the points along that path, and then you will multiply by the magnitude of the velocity and then integrate with respect to t. And it was this quantity here which we called ds. So this has the units, this ds has the units of length, right? Has units of length. Velocity times time is equal to distance. Velocity times time is equal to distance and length. And this function has the units of, say, kilograms per meter, a density function. So kilograms per meter times something in meters gives you the units of kilograms. So that is the interpretation of these scalar integral functions. The next step is just to evaluate them, and then we will move on to other types of line integrals called line integrals of vector fields.